Hey there, this is Warner and this is the FPM Pre-Test. And so what we'll do is we're going to go ahead and go through each one of these problems. We do have this flower pot, it's 22 newtons, it's hanging by 4 ropes. So one of the things we're going to do is we're going to add another rope in there, just in the back. And they each make a 12-degree angle with the vertical. So first thing we need to do is go ahead and let's draw our free body diagram. So this is MG here. And then let's just draw one of the ropes. Because there's more than 2 things, you really need to make sure you only draw one and then multiply everything by 4. So we've got that. Let's go ahead and let's make our components coming straight across there. We know that this angle is 12 degrees, and so we've got it. And other than that, we just need to put in what this is. It's force times force of tension. So the top will be Ft, and then we're going to do sine of the angle, so sine of 12. Why? Because this is the opposite side. This one will be Ft, and this will be cosine of 12 degrees. So now that we have everything ready in our diagram, we can go ahead and start doing the sum of the forces. I'm going to change the pen so that it's a little bit thinner here, and I think that'll help. All right, here we go. So we're going to say sum of the forces in the y direction are equal to 0. Now, because we only have the y direction, you could just put sum of the forces are equal to 0. Remember, this represents just one of the 4 strings, so we need to do all 4. So let's do that. Here we go. We're going to say 4 times, and notice that this is the y direction, Ft cosine of 12 is equal to, because, oops, sorry, we want to say minus, so let's back one off here. So this will be minus mg, and that's equal to 0. So how do I know that this is positive and this is negative? Well, we need to draw an axis here. This is positive y, and then this is positive x. Now that we've done that, we can go ahead and solve. So we're going to say Ft is equal to, and then we have mg, because we added mg to both sides. Then we need to go ahead and divide by that 4 times the cosine of 12. At this point, we have everything we need. We know that it's 22 newtons, so 22 newtons would be both mass times gravity. So this is 22, and we're going to divide that by 4 times the cosine of 12, and you should end up with 5.62 newtons. So that's the first problem. Let's go ahead and take a look at that second problem. So we're going to clear the sheet, come over here, move everything down, oops. And so basically what I want to do here is get rid of all of this, clear the sheet, and now I just want to move everything. So I'm going to minimize that guy, move this up. And this is an incline problem. So remember, incline problems, you have to make sure that you draw your free body diagram first, and then draw another free body diagram that actually has all of the components. So that's the instructions that were on the sheet. I know for the first one you didn't have to do that, but for this one I really think you should. So let's go ahead and start this one. Let's draw our free body diagram. So we've got our dot, and straight down is going to be the mass of the box times gravity, up and to the left. So remember, this is our incline. So everything needs to be perpendicular to the incline in terms of the normal force. So that's the normal force. We also have a force of friction. So this is the force of friction that is pointing up the hill, that's keeping the box from coming down the hill. Now that we've done that, we have all of the forces. So that's the first diagram. Our second diagram is the same thing. So we'll draw our incline. Here is the normal force. Here is the force of friction. And then we have mg pointing down. So I'm going to draw the incline here, and then I'm also going to put in the angle theta. So there's our angle. At this point, we need to draw our components. So let's go ahead and we'll switch colors. We're going to switch over here to black. I want to draw one that is going in this direction. So notice it is in the same line as Fn, but more importantly, it is perpendicular to our surface. We're going to say that in this direction, we have positive y, and then in this direction, we're going to say this is positive x. So now we have something in the y. Let's also make something in the x direction. So those are your two components that you want. So we'll go back to our blue pen again. This angle right here is the same as this angle by geometry. So we want to make sure that that's correct. Next thing we need to do is go ahead and put in mg, cosine of the angle, and this one is mg times the sine of the angle. So y again, this is the adjacent side, there's our opposite side. So now we have everything we need to go ahead and start solving the problem. For the normal force acting on the box, notice that it is in the y direction. So we want to say the sum of the forces in the y direction are all equal to 0. We know if we put our pencil here and move back and forth right on this ramp, we see the only thing going up is Fn, so we're going to write it first. And then we put it below the ramp and we notice that the only thing pointing down is mg cosine of the angle. So we're going to be minus mg times the cosine of the angle, and that's equal to 0. That means that the normal force is equal to mg times the cosine of the angle. They told us that the angle is 42 degrees. They also told us the mass of the box is 24 kilograms. So let's go ahead and put everything into our equation. So we're going to say Fn is equal to 24 times 10 times the cosine of the angle, which is 42 degrees. If you do your math for this, you get 178.4 newtons, and that is the normal force. So we've done the first part. Let's go ahead and do the second part. After we answer what type of friction is holding the box on the hill, this is called static friction. So remember, static friction allows things to be stable or static, and then kinetic friction is the friction of movement. Let's go ahead and do the other one. So this is for the sum of the forces in the x direction, and it is also equal to 0. For this one, we notice that we have mg sine of the angle going in the positive, mg sine of the angle, and then we need to subtract from that, so we put our pencil here now. This is mg sine of the angle, and then if we put our pencil here and look, we have force of friction, so this is minus the force of friction, and that's equal to 0. Let's go ahead and solve for force of friction. Mg sine of the angle is equal to the force of friction. So now we're set. Let's go ahead and plug all of our numbers in. So this will be 24 times 10 times the sine of our angle, which is 42, and that's equal to the force of friction. If you do your math, you should end up with 160.6 newtons, and that is equal to our force of friction. So that is the second problem. We need to go ahead and we need to switch over to the third problem. All right, here we go. This is number 3. In the figure, we've got a wrecking ball. It's being held over to the side so that it can be released and then come over and knock down a building. And we have tension in a rope that is up to the crane that it's being held up by, and then we have weight on the way down. So let's go ahead and make our free body diagram for this one. We're going to draw a dot here, and we know that straight down is mg. We know over to the right, we're going to call this one ft, and we're going to call it 2. It's going to be different than the one that we have going this way, which is ft1. So that's the difference between the two, because this one is at an angle and this one is straight across. They will have a different tension. We need to now draw our diagram again. So this is mg. This one is ft2. And then this one is ft1. Let's go ahead and put our components on. So remember, your components need to have some sort of axes. So we're going to say straight up is going to be positive y, and then let's make over to the right positive x. So here are our components, one here and one here. Notice that they've asked for the angle up at the top, not the one for the dot. So we're going to actually put it right there. So we're going to do this, and then let's go ahead and put our angle in. So our angle here is theta. So that's a little different than what we've done in some of the others, because usually we have the angle down by the dot. This time we don't. But it's not a big deal. We've got the opposite side, so this will be ft times the sine of the angle. This one is ft1 times the cosine of the angle. So now we have everything we need in order to solve the problem. Let's go ahead and solve that problem. Let's talk about the sum of the forces in the x direction first. So sum of the forces in the x direction are equal to 0. Anytime you do the x direction, put it in the positive first. So here is from the dot over to the right, we can move it in a vertical fashion. We see the only thing here is just ft2. We're going to subtract from that anything that's going to the left on the other side, and the only thing we have going to the left is ft1 sine of the angle. So this is ft1 sine of the angle, and those are equal to 0. Let's go ahead and solve for this. So now we have ft2 is equal to ft1 sine of the angle. So there's not much more we can do with that one. Let's go ahead and let's set this up so that we can solve a little bit more. To do that, we need to do sum of the forces in the y direction. So I'm going to actually do that over here. Sum of the forces in the y direction are equal to 0. For the y direction, we want to find out what is it that's pointing up. It's ft1, cosine of the angle, and we're going to subtract from that anything that's on the way down. Notice that that's just mg, so this is mg is equal to 0. And so now we know ft1 cosine of the angle is equal to mg. Now that we've done that, we can look and see that we do have ft1 cosine of the angle is equal to mg. And so let's solve this for ft1. We're going to say this is ft1 is equal to mg all over the cosine of the angle. Why did we do that? Well, our problem is we have an equation with two unknowns here, or we actually have one of the things that we know. Let's go ahead and we'll plug in here this ft1, and we're going to plug it in up on this diagram here. This will help us find the angle. So we're going to take what's in ft1, which is right here, and we're going to plug it into this one. So now we have ft2 is equal to mg over the cosine of the angle. So this is mg over the cosine of the angle. And then on the top, notice that we have sine of the angle still. So we just took for ft1, we know that's it. We take this, plug it in, and we end up with this. Remember your trig identities. We know that if I want tangent of an angle, one of the identities is we can do sine of the angle over cosine of the angle. So that's really important to see. So now this becomes ft2 is equal to mg times the tangent of the angle. So what do we already know about all these? We already know ft2. We know that that's 6372, and we know that the mg is 12,400. So we'll just put that in over here, 12,400. Because of that, we can say that the tangent of the angle is equal to ft2 over mg. And then we can divide both sides by tangent, and we end up with the inverse tangent. So here the angle is equal to the inverse tangent of ft2 over mg. So that's equal to the inverse tangent of ft2, which we said was 6372, divided by 12,400. You plug that into your calculator, and as long as you're in degrees, you're going to end up with our angle. And our angle then is going to be equal to, yeah, that's right, 27.2 degrees. So that's a 27.2 degrees. I guess I can erase that and make it look a little bit better. So let's get rid of that, and let's redo the number here so you can read it. So this is 27.2 degrees. Now that we have the 27.2 degrees, we can go ahead and we can solve for FT1. So remember, FT1 is mg times over the cosine of the angle. So we're going to do FT1 is equal to mg, which we said was 12,400. And we're going to divide that by the cosine of the angle that we just found, which is 27.2 degrees. If you divide those two, you do end up with 13,942 newtons. So there is your FT1 calculation. Here is the angle that they wanted you to calculate. We only have one more problem to do, so let's go ahead and do it. We'll go ahead and clear the sheet off again, and we'll go ahead and minimize this so we can move this up. This is a skier, and the skier is going down the hill, down to the left. They want us to find a couple of things. One of those things they want us to find is the normal force of the skier, and they also want us to find the friction keeping him from accelerating down the hill. We need two diagrams. So here's our first diagram. We're going to draw a line straight down. This is the weight of the skier. We know this is our incline, so we'll put it there. Here is our normal force. And then here is our force of friction. So we've got everything in our diagram. Let's go ahead and say that up in this direction is positive y. And we will make, because the skier is going down the hill, let's make this way positive x. Let's go ahead and draw the free body diagram again, but we'll put components on it. So this is Fn. In this direction we have Ff, and then straight down we have Mg. Remember, our incline is right here. And typically what I tell people is make sure that you don't put any components on that incline. So instead, what we'll do is we're going to put our components here, so that matches the y, and here, and that one matches the x. So at this point, we can go ahead and write in what our components are. We're going to move the mg over so it's not in our way. And we're going to come back up here. So this is mg, is this line. This is going to be our angle right here. It's with the dot. That always makes it easier. This is mg times the sine of the angle. And this one is mg times the cosine of the angle. So now we have everything we need in order to solve this problem. We're going to look at it in both the x and the y direction, so we can find both the friction and the normal force. So usually when they ask you two things, it's probably because they want to make sure you can solve in both the x and the y direction. So here we go. We're going to say sum of the forces in the x direction is equal to 0, and sum of the forces in the y direction is also equal to 0. Because this thing is traveling at a constant speed or a constant velocity, and it's keeping him from accelerating down, so he's not accelerating. Some of the forces in the x, remember down is positive, so we're going to look here and we see that it is mg sine of the angle. So we'll write it in first, minus, and then we have force of friction going in the opposite direction. That's equal to 0. So our force of friction here is just equal to mg times the sine of the angle. Our mg, notice that we have not weight this time, we only have mass. So that's 50 times 10 times the sine of the angle. And we said that the angle here is 35 degrees. So this one says 35, it's actually 22 is what you have on your worksheet. So we're going to change that to 22 degrees. So that is the sine of 22. So now we have 500 times the sine of 22, and that equals 187 newtons. And that would be equal to our force of friction. We also need to do this in the y direction. So when we do this in the y direction, Notice up is positive, so the only thing we have anywhere left to right here going up is the normal force. So there's the normal force minus everything going down, which is mg cosine of the angle, and that's equal to 0. We'll go ahead and plug everything in now after we solve it for Fn. So that's mg cosine of the angle. Mg is 500 or 50 times 10. And then we're going to do that times the cosine of 22 degrees, because remember we changed that angle for this worksheet or pretest. So that's 500 times the cosine of 22, and that will be our normal force, and that ends up being 464 newtons. I hope you've enjoyed your time, and hopefully you are going to repeat all these things for your test on Thursday.